Okay. So since this is the last day, I'm going to try to introduce as little new material as possible. Also, I have only one lecture. And the goal of the lectures basically is going to be to provide a lattice Hamiltonian realization of this SymTFT picture that was mentioned in a few lectures and talks, using some of the formalism that Yifan introduced yesterday and today. And I'm going to use that to revisit the examples that Shureng talked about, so the cluster state model in particular. So let me start by listing some of the kind of sort of mathematical constructions that we're going to use, and then I will explain a bit more the physics picture. So the focus is going to be 1 + 1 dimensional systems, and it was already established in several lectures that if we're focusing on finite, possibly non-invertible symmetries, so in 1 + 1D, then a good framework in order to describe the collection of topological lines is given by the theory of fusion category. So the collection of topological lines is going to be given by a fusion category. I'm going to add an adjective that maybe I will use later if I'm talking about the SymTFT picture. And so a fusion category, I'm going to call C. There are several, there is several pieces of data entering the definition. In particular, we have a category. We have a tensor product, which allows us to fuse topological lines. And we have, in particular, these F symbols, right? And this F symbol, they allow you to recouple lines in the following way. So these are the so-called F moves. So this is what Yifan explained yesterday. So these correspond to, as was explained, if you look at a junction space like this involving 4 lines, you can split it in different ways. These correspond to different bases of the junction space, and this is the change of basis.
Yeah, when I say topological line here, do you I think that means the symmetry defect line. Right?
That's everything. It's going to be the operators.
The borderline of charge.
Here, by topological lines, I'm including both, I would say, what I call symmetry defects and symmetry operators. So it's going to be both the operators acting on the Hilbert space and also the ones twisting the Hilbert space. That's what it accounts for.
Yeah, but whether there's a borderline of symmetry representation of the...
You mean the charge operator?
The charge operator. No. Oh, I see. Oh, thank you.
Okay. And we learned also today about a gaugeable collection of lines. So when you have a corresponding fusion category symmetry, you can gauge some of it. And this is encapsulated in, so what Yifan explained earlier, a symmetric Frobenius algebra. I won't worry too much about the symmetric and Frobenius part, but the algebraic part is important. So there is in particular, so there are additional stuff, but I'm going to focus mainly on this, what was written A and M before. A is really the collection of lines. So this is an object in the category. It's going to be a direct, so it's typically not a simple line. It can be a direct sum of simple lines, which corresponds to a non-simple object in the category. And you have a multiplication, which gives you access to junctions of such lines. So again, in the case of an invertible symmetry, this junction encodes the choice of discrete torsion, for instance. This gives you access to the twisted gauging that were considered before. Yifan also briefly mentioned earlier that so this characterization of sort of what amount of symmetry you can gauge, which is provided. So here we have a kind of a classification provided by these algebra objects. There is an equivalent way of characterizing how much symmetry you can gauge given by module category. So let me briefly introduce this notion. So again, I'm adding some adjectives that are required, but we won't worry too much about it in these lectures. And so I define a right C module category. So M with some additional information. And so what it is, so it's a category in particular, and it's a category equipped with an action. So there is an action of C on M. Yep. And also, we have a bit in the same spirit as when you define the fusion category, where you have a tensor product, and then you have these F symbols that allow you to recouple the lines. We're going to have something equivalent for module category, which is this object referred to as a module associator. And what it allows you to do is something very analogous. So here in this picture, the lines that I'm representing on the left, like a straight line like this, these are lines in the module category M, right? So this I cannot, it's not necessarily a fusion category, so I cannot fuse these lines together, but I can act with the lines in C on these lines in M. So the lines on the right here are in C, right? And this action there, it gives us, this action there gives us access to this type of junction spaces involving two lines in M and one line in C. And so this moves then these F symbols, which are slightly different F symbols. They allow you to, once again, you have a junction space here, junction space involving 4 lines. You can choose 2 different bases for the junction space, and this encodes the change of basis of this junction space. Okay. Maybe I can briefly sketch the connection between the two notions, how you can establish. So the idea is that whenever you have an algebra object, you can build a module category, and whenever there is a module category, there is a way of constructing an algebra object from it, or there is a corresponding algebra object. The relation between the two, which we're not going to use explicitly, but let me very briefly write it, is given by the notion of left module object in a category. So a left module object consists of 2 things. It's an object in the category. So again, it's like a collection of lines. And these are lines on which you can terminate the lines that are encoded in the algebra A. So you have a notion of junction between the lines in A and the lines in this object M. Now the relation between the two, so the idea is that if you look at the category of such lines, so the category of left A module objects form a right C module category. So this is what I was saying earlier. Given an algebra object, you can always construct the corresponding module category. The proof in one line is the following. Let's say I have an object there, I have a left module object M, okay, and I'm tensoring it with an object X, so X is in C. I'm tensoring with an object X, okay. And what I want to show, so this I'm claiming that this is going to be the action, this is going to be the action of the corresponding module category, and I'm claiming that this thing is still going to be a left module object. So the way to prove that is that you just tensor with A on the left. Then you can use this type of associator. You can change the order in which you do things. This is what gives this F symbol, this is what it gives you access to. So you can rather do this instead. At which point you can just use the defining property. So I can use P over here to write M times X. And so this is the defining condition of being a left module object. So this is just the relation between the two. We're not going to exploit it explicitly. What I want to emphasize though is that both, so these algebras of lines and this module category, so as I said again, they capture the same information, which is what you can gauge in your theory. However, physically, they don't exactly encapsulate the same thing. These algebra objects really correspond to the lines that you couple with your theory, right? And then you sum over these lines, you make them dynamical, and this is really what performs the gauging. This module category, especially in the lattice setting, they will rather correspond to the effective. So once you do the gauging, you have, let's say, you create some Gauss constraints that then you can solve to define an effective field theory, and the degrees of freedom of this effective theory will be given by the module category. So they don't correspond to exactly the same type of physical information, at least in the lattice setting. Yeah.
So in this picture of half gauging that Ethan was explaining, these things are junctions between the Algebra object on the ungauge theory and the topological defect line that you get by fast gauging?
Yeah. Actually, I'm going to give a slightly more general picture where you can imagine where, let's say you do some gauging on one side and then some gauging on the other side, and you might want to capture what the interface is between the two. So you need somehow something that relates two different possibilities of gauging. And this is going to be given, so this is the last thing I want to introduce. This is going to be given by, so essentially a notion of map between module categories, something that relates them. And this is what we call a module functor. So given C module categories, so two of them, which corresponds to two different ways of gauging, let's say. They could be the same, but they could be different, M and N. A C module functor between them, so there are two pieces between them, consists of the following thing. We have essentially just a map between the corresponding module category. It's just a way of relating essentially the lines encoding in one module category to another. So there is a relation between the two. And this relation needs to be compatible with the action. It has to be compatible with the module structure. In a way, you want that when you apply this map, it should commute with the action of a line in C. And so this is encoded in these isomorphisms omega here. And graphically, you can represent it like this in the same spirit as the other symbols we introduced so far. Something that looks like this. So the line in the middle, in the spirit of this diagram, these are going to be given by lines in the module categories. At the top, we have a line in M, and at the bottom, we have a line in the other module category. And actually, this one here is also in the module category N, because by this diagram, what I mean is that this is essentially the action of F on this line. So it's a way of transforming a line in M into a line in N. So this is what it's represented by this diagram. Here, this is the action of an object in C. Okay. So then this is another type of junction spaces, right, involving, again, 4 lines. And to some extent here, I chose a basis for this junction space involving lines in M, lines in N, C, and also this operator that allows you to transform a line into another. You can make a different choice of basis, which is encoded into such a diagram. Okay, so here you see essentially the idea is that you can first act with X and then applying the map F, or you can do it the other way around. It should commute. You should have an isomorphism. I forgot to mention, well, it was already mentioned, but so these F symbols, they have to satisfy some consistency conditions, these pentagon equations. These also have to satisfy a very similar looking pentagon equation, so a pentagon axiom. And I invite you to write down explicitly this axiom. And this will involve not just, so the pentagon axiom of F only involves F's. You know, it's like 3 F's on one side, 2 F's on the other side. This one is going to involve not just this F with the triangle with the action, but it's also going to involve the one in C. And if you remember the logic that led you to the pentagon axiom in the case of a fusion category, you can apply the same logic there and recover very easily this pentagon axiom. This one will also satisfy a pentagon axiom, which I won't write down explicitly. Again, applying the same logic. And this one it will involve the symbols, the moduli associator of both M and N. It's a compatibility condition involving a little bit everything. Okay, so this.
There is a question.
Oh, yeah, sorry.
Can you explain why the model object belongs to the object of the category?
Yeah, so by this notation, I don't remember if this notation was used before, but so here I'm just saying that this is an object in the category, right? So literally, this is just going to be a collection of lines. Typically, maybe not a simple line, but it can be a direct sum of lines.
So you're saying the objects that can be condensed by that model object. Is that what you're saying?
So here, these are certain lines on which you can, the ones that you gauge can terminate. And thus it gives you access to a diagram of this form. A diagram of this form.
Clement.
Yeah, sorry.
Are all module categories over C of that form?
Yes. You can. So there is a slight, slight caveat, I would say, is that several algebra objects can give you several module category because we're computing modules, which means like if you have a notion of Morita equivalence, you can have like algebras that look slightly different, and then they have the same modules. In that case, they would live to the. So the one-to-one correspondence is more like between like kind of Morita class of algebra objects and then module category. But yes, there is a procedure actually given the module category to work out which algebra object will give you the module category by applying this construction there. Yeah. Okay, so what this, so in practice on the lattice, and I'm getting there in a second, this module functor, they will give us access to two things. They will give us access to essentially, so in the spirit of what I just said, of operators relating theories that have, for which we gauged a different amount of the symmetry. And so in particular, if let's say you can always choose the module category, you can always choose a module category to be the category itself. Right? The module category to be itself. In that case, these symbols, it's just literally the fusion category. This amounts to not doing any gauging if you want. And then if you choose something else, then it amounts to doing a gauging. If now I will look at the maps between, so in that case, it would be C and another module category. This will give us access to the operators, literally performing this gauging on the lattice, for instance. If I focus on the case where I'm choosing the same module category before and after, this will give you access to sort of interfaces, but within the same half of the space where I did my gauging, and this will actually give you the lines, the symmetry lines that you have after gauging. So this is the last thing I want to mention, the dual symmetry after gauging. Is given by what we call the Morita dual of the category with respect to a truss of module category. So this is what we call the Morita dual. It's called dual because there is a notion of equivalence of C with respect to M. And this is defined as the category of all module functors from M to M. Okay, so all objects of this type, where you choose the same M on the left and on the right, this will give us the new symmetry. It will give you the new symmetry after gauging. And indeed, like when you gauge like a finite, discrete symmetry, you sort of, if you want, losing part of the symmetry, but then you're gaining another dual symmetry. And this is with this mathematical construction. This will give you the resulting symmetry. So let me do an example. Yeah. Well, yeah. Okay. Let's start.
In the case of group-like symmetries, to do that, you need
I was gonna
to have a normal subgroup. Okay.
No. You do well. I'm just gonna do it. Yeah.
Okay.
When you said that M is the category C itself, then the C module functor told you the operators used to implement the gauging. What does it mean for an operator to implement the gauging?
I will do an example.
Oh.
Yeah. At the very end. Yeah. So let me do an example. Okay, so when we talk about ordinary symmetries, as was mentioned before, the relevant category is this category that we write vec G. So here there is no anomaly. Okay, there is no anomaly. The only thing you gain by thinking about the ordinary symmetry in terms of this category rather than just thinking of the group is that you have, we've been mentioning several times that you want to be able to consider direct sum of lines. Okay, you can't take direct sum of group elements, so you need to add some linear structure to your algebraic structure. But essentially, you want to endow your group elements with some structure of some vector space, and then once you have access to vector spaces, it makes sense to take a direct sum, right? So in a way, loosely speaking, the idea is that we're going to kind of assimilate a group element rather with a one-dimensional vector space that is going to be labeled by this group element, but now that it's a vector space, I have additional structure. That's the only point of using this at this point. So in this category, then the algebra objects, they're always of the form so we have two elements. There is a subgroup. So this subgroup does not have to be normal. It can be any subgroup. And then psi is some representative of a cohomology class, which represents the discrete torsion associated with this gauging. Okay. So if I choose A and psi, I'm doing the twisted gauging of the subsymmetry A. Now, specifically, so maybe let me briefly emphasize this if it was unclear from the previous lectures. Given a subgroup, the corresponding algebra object is going to be the sum of the corresponding lines labeled by group elements in that subgroup. Okay, so I'm using here, like, again, I need to have a direct sum, so I'm using this notation I just introduced. And then the multiplication of, if you want, the multiplication of the algebra part of this object, it's the usual group multiplication, but it's going to be twisted by the two cocycle. So maybe to clarify, when you have the junction space, what was drawn in the before, when you have a junction space like this involving your algebra A everywhere, in the group case, here I have a one-dimensional junction space for a given, like once I pick a basis, some basis element in this algebra, the junction space is going to be one-dimensional, right? Because the multiplication, when you multiply group elements, there is only one possible output, so it's one-dimensional junction space. But you have some freedom. You can choose some phase there. This is what this psi encapsulates. Okay, you can choose this freedom there. Now, what is crucial is that the corresponding module categories associated with these choices are usually written MA psi. And so, for instance, let me do two examples. If I don't gauge anything, so I'm choosing the trivial subgroup, and then I have no choice of two cocycle. The corresponding category, as a category, is the category itself. So this is the case I mentioned before. This is the case we can always choose. We can always choose as a module category the category itself, which means we can always not gauge anything. That's obviously the case. What is more problematic is whether you can actually gauge something. When there is no anomaly, we can gauge everything. Okay, we can gauge everything, and in that case, as a category, what you get, well, you get a category that is kind of trivial. This is this category we write vec. It's a category of vector spaces. What is important here is that this is a category with a unique simple object. So this is really just having, if you want, the vacuum. There is only one line in this category. It's just the one labeled by the identity, if you want, the vacuum. But, so this amounts to gauging everything. We'll see how it works exactly on the lattice. But you can do it, you can gauge everything, and there is a choice of discrete torsion you can make. And so I'm keeping track of this choice of discrete torsion here. Because this, what it does, is that this will change a little bit. The F symbol there will depend on the choice of psi. I will show an example, a concrete example later.
Can you write a no anomaly condition in this language?
So here there is no anomaly because there is no, there would be an anomaly if I were to add something here, which would be a 3 cocycle, and this 3 cocycle would give you an F symbol, right? Yeah. Once you have this, the algebra, so this was not emphasized so much, but the algebra needs to be associative in the category, and in particular, this associativity condition involves this. And if you have a non-trivial 3 cocycle there, then there is no way you can do this, because this would amount to saying that the associativity would imply that this is trivial. But if you choose it to be non-trivial, then it's not possible. Yeah.
Can I always think of the module category as what survives the gauging?
This will be exactly, especially on the lattice, this is exactly true. This is what I meant earlier, is that so once you do the gauging, then usually you have, you insert your gauge field. Like you basically insert this network of built from the algebra objects. It's like inserting a gauge field. Then you have some Gauss constraints. So you have a Hilbert space that is much bigger initially than the one, much bigger than the initial one. And then you can say, okay, let's solve the Gauss constraints, right, as much as possible. And what you're left, your matter degrees of freedom, if you want, if they were like given by G at first, now they're going to be given by the quotient actually of G by A. So this is indeed literally what's left after you perform the gauging. Yeah. Okay, and so what is so let's say considering this case, right? What happens to the symmetry? I'm just going to put it there. What happens to the symmetry after you gauge? So everything in particular. So what we are interested in is the dual of vec_g with respect to this vec psi. So it's there is potentially a choice of discrete torsion, and this is equivalent. It's an interesting computation actually to do. It's equivalent to the category of representations of the group, right? So you're trading an invertible symmetry given by a non-abelian group, let's say, by a non-invertible symmetry where the topological lines are now labeled by representations of your group. And importantly, the choice of discrete torsion does not show up here. You always get the same dual symmetry regardless of the choice of torsion. It will change what is your dual theory, but it will not change the dual symmetry of this gauge of the theory you obtain after the gauging. Okay, so yeah.
So again, what is the interpretation of M in this case?
Which one? This one?
The left.
For the module, this one there? Yes. Yeah, so this really, it should be much clearer once I show how you construct lattice models from this. But this will literally correspond to the degrees of freedom of your model. I think it will be clearer if I just show the construction first, because it's.
So it's not an interface.
So that's the thing that is a little bit tricky, is that in this. The same information module categories represent many different things depending on the context you're interested in. So there is a scenario where indeed it represents an interface. Actually, like in the case where you, let's say you don't do any gauging and then you do half gauging on the other side, right? So what you're looking for is basically a map between C and the module category. In that case, this map is also, the maps you can put there are classified by M itself. In that case, this is a scenario where M literally represents the interface between not gauging and gauging. Now I'm going to use it in a slightly different way, where there M will provide really the degrees of freedom of my lattice model. Okay, so let's do this. Yeah.
Can you show an example when A is a proper, non-trivial, preferably non-normal subgroup?
I mean, you mean like what is the dual symmetry? You mean?
The rep A times G mod A, but I think this doesn't work when A is not normal. That's why I was.
So there is a general form. Actually, let me just put it there. So generally speaking, let's say I'm doing a gauging. So A is really arbitrary here. Taking any possible A. So this category, actually, there is a formula. Okay. And here, actually, in that case, the twist does not necessarily disappear, so you have a contribution there. So there is a general formula. Yeah, the thing it's a formula as a category. It just gives you the information as a category, the collection of lines. It doesn't necessarily give you more structure than that. So you have to work harder if you want more to know more about this category. So in particular, if you want to know what it is as a fusion category, you have to work much harder.
Yes.
Yeah.
If an elementary question, given a specific A, how is it? Can we know that M is unique?
So given a specific, so as I mentioned before, you can have several A's that give rise to the same M, because if they are Morita equivalent, it means they have the same simple module. So in that case, they will share the same. They will share the same module category.
But for one A, you always get one M.
Well, yeah, I mean it's a constructive. Yeah, because there is really a construction, right? So yeah.
When A is normal, does this formula simplify in any nice way?
When it's normal, it makes a lot easier to compute what is the fusion structure of that thing. When it's not normal, it's significantly more complicated. Yeah, but otherwise, this not really. I mean, it's already quite simple. I mean, I don't think you can really simplify it much more than this. Yeah. Okay, so let's now let's stop with the math and let's do some physics. So now let me show how we can use that to build the lattice models. So basically, we're going to build lattice models where it's easy to identify what the symmetry is, even when you have potentially non-invertible symmetry, and where it's also easy to perform the gauging of these non-invertible symmetries. So Schoring mentioned briefly this framework before. It's known as the anionic chain construction. I'm going to present a generalized version of it. So let me share a few references here. So this construction was first established for the case of the Fibonacci category that you heard about this morning. So in this paper. 2007, there were several generalizations of this construction. Eventually, there was one for arbitrary fusion categories. And I'm going to use the generalization that we introduced in that paper, which incorporates in particular this module category data. Okay, so what is the input of, so the goal now is to build a lattice model that is going to have a given non-invertible symmetry. So the input of this model is given by the following. So first we're on 1 plus 1D, so we need a lattice, which is going to we're going to take it to be a closed 1D chain with L sites. Okay. Now I need a fusion category. This will dictate the symmetry, essentially, at least up to equivalence, up to gauging, I would say. Now I need to choose a C-module category. So this C-module category will dictate how much of the symmetry I'm gauging. We need also a collection of lines, so just an object in the category. This will dictate what the Hilbert space of the model look like. And finally, I need something that will encode the dynamics of the theory. And this is, so let me first write it down like this. It's a map in the category, which corresponds just to a vector in a given junction space. So here, I'm considering a map from an n copies of the object x to n copies of the object x. Typically, we choose n to be 2. So this will basically dictate on how many sites you act, whether you want a 2-body, 3-body, 4-body term in your Hamiltonian. So typically with 2, we can already cover like most Hamiltonians. And so this thing, how it looks like exactly? Well, it's just another type of junction space that looks like this, where I have the 4 lines labeled by my object x, which again, this object x is not necessarily simple, right? It can be like a direct sum of lines. And here h is just a vector in this junction space. Okay, so that's the input. And this will encode the Hamiltonian, but at this point it's literally just a vector in the junction space. I haven't explained yet how you turn this into a Hamiltonian, but I'm going to do that right now. But in order to do that, I first need to specify what the Hilbert space is. Okay, so the Hilbert space is going to be, we're going to fully rely on the graphical calculus. It's going to be defined as some, if you want, some formal linear combinations of diagrams that are decorated by objects and vectors in some junction spaces. So concretely, it looks like this. It's going to be spanned by objects of this form. So I'm working with a closed sort of periodic boundary condition, so I'm using this symbol to represent that. Okay, so this is what my diagrams look like. So these are like tree-like diagrams, and this is really the same graphical calculus as before. The lines at the top, they are all labeled by x. This is why I was saying that x dictates the choice of Hilbert space.
What is epsilon? Span epsilon?
No, it's... I don't know why it looks like an epsilon. Okay, and the lines at the bottom, they are labeled by simple objects in my module category. Okay, so now I have junction spaces involving 2 objects in the module category, 1 object in X. So these are junction spaces of the type I had here, right? And so I can choose some vectors in these junction spaces in particular, which I'm going to write by F. So the span is over objects in the module category, and then vectors in the corresponding Hom spaces. If you want, there is a more precise way of writing this, a more formal way. I'll just put it there in case you find it more useful. Okay, so it's actually a direct sum of these are the junction spaces that you have here at these intersections. And because of the direct sum here, clearly this thing is in general not a tensor product. It is possible that sometimes it is a tensor product, but in general it wouldn't be.
Sorry, there is a tensor product missing in the last line? Do you want?
Yeah, sorry, yeah.
Do you know the general condition on the C and module category in the cases when it's a tensor product, the Hilbert species?
Yeah, so that's a great question. So if I choose M to be vec, which you cannot always choose, as I was explained, if you have an anomaly, and in principle you cannot. If M is vec, I will do this example later, but like indeed, then you sort of forget about all the M's, then it's all about the X's there, and so clearly they are kind of decoupled, so it's clearly a tensor product. It is possible, however, to have a tensor product even when you cannot choose M as a module category, and there it's a bit more case by case. I don't know of a general rule when this, but this is a good question.
But why is it such a big deal, tensor product? Not? You can always take the tensor product and then add a term in the Hamiltonian, which is going to forbid all local terms.
You can do that. Now, of course, the action of the symmetries may not necessarily be very well defined, because you will rely, the action of the symmetry lines will, in some cases, really, it will only be well defined if you have these conditions that are satisfied everywhere. So you can, in some cases, you can make it dynamical indeed. You can incorporate in the Hamiltonian, but not always. And it's not really clear in which cases you can and which cases you can. Yeah. I think there was another question. No?
Also, is it possible to enlarge the Hilbert space so that the enlarged Hilbert space is tensor product and this restrict the?
I think it's a bit related to Slava's point. Like you can, I think it would amount to make it dynamical. So then indeed you can enlarge it in various ways. It's certainly possible in some cases, but I don't think it's possible always. Yeah.
Sorry? So you have to sum over all the possible F's, is it right?
Yeah, so this Hom, no, this is the vector space sitting there. So then basically I'm taking here like some direct sum tensor product of vector spaces, okay? So so basically it amounts to choosing the M's, and then once I chose the M's, I can still choose some basis vectors in these spaces over there.
Yeah. Is it understood that like, with choices of X will give you equivalent models?
So, in the sense of dual models, you mean?
Well, I guess like I would imagine different choices of X like sometimes will be the same, like literally the same like today's diagram.
So it's certainly possible to realize a given model in different ways. Like if you have a specific model in mind, there are typically many ways. You can start from a different fusion category, a different module category, a different X. There is some freedom there. Of course, the symmetry is fixed, so it has to. I forgot to put M here. The symmetry is going to be detected by the dual of C with respect to M, so this has to be equivalent to the symmetry you're after, but you still have a lot of freedom. Again, in general, it's not clear what are exactly the,
In particular, you're not requiring X to be simple.
X is typically not simple, yeah. But sometimes it is. I mean, if it's a one-dimensional object, if it's simple, it's not going to be super interesting. But if it's a higher dimensional object, then fixing X to be simple, then it's actually sometimes you can get Heisenberg model like this actually. So it's definitely, yeah. Okay, so now the Hamiltonian operator. So basically it's going to be how does that thing act on that thing? So the Hamiltonian operator in general, just like a sum of local operators, where HI essentially acts trivially away from the site I, but in some neighborhood of I is going to act non-trivially. And it acts non-trivially, I'm going to put it there, in the following way. So by definition, so I'm restricting to the case where n equals 2 there. So given this choice, then it can only act non-trivially or depend on the degrees of freedom that are located in the immediate neighborhood of I. So I can forget about the rest, I can focus on this piece. Okay. And it acts in the following way by just stacking that thing on top, essentially. So at this point, the degrees of freedom at the bottom, they are completely unaffected, and they're exactly the same. Okay. So let me explain a little bit this picture. So this, again, this guy is a junction space involving 4 lines. Here, by sort of splitting this 4-valent junction space in this following way, we are making a choice of bases. So this guy labeled by choosing m's and vectors in these Hom spaces, you capture all possible vectors in the 4-valent junction space. So this is my choice of basis. Now this thing, if I look at this sort of blob around here, well, this is the same junction space, right? It involves the same 4 lines, mi minus 1, xx, and mi plus 1. And this is just like this kind of diagram in the middle represents like a specific vector in this junction space. What you want in order to write down more explicitly the action of this Hamiltonian, you basically want to rewrite this vector in this basis. This is essentially what we want to do. So to do that, you can do it very explicitly. It is convenient to choose a specific basis for this junction space. So same story, to choose a basis there, I can split my 4-valent junction space in various ways. I'm going to do it in the following way. Okay, I can rewrite it like this, where I have a sum over some simple object in C, and then some basis vectors. I have some complex coefficients here. So I'm expressing a vector in a basis. So I have the corresponding coefficients. And I chose this way of splitting the 4-valent vertex. So I'm choosing this basis for this junction space. Now I'm just writing an arbitrary vector in this basis. Okay. So once you have this, I'm going to do it sort of graphically. The action of the Hamiltonian. You proceed as follows. So we are at this stage. I'm just rewriting this part in this expanded form. Okay, I'm not putting the labels. I'm just going to do it heuristically. And then, so just to be clear, the labels here are all in M. The labels here are all in C. Okay. And then I'm going to use my moves here, the moves that are still drawn over there, sort of these recoupling moves, which just amount to change of basis. And so here I'm going to do several changes of basis until I reach the basis by my initial basis. So the first move I'm going to do the inverse of the move involving the modular associator of M. It's going to look like this. Okay. And then I'm doing another move, still involving the modular associator, and I end up with something that looks like that. Okay. At this point, I can just use sort of orthogonality of the basis vectors in the junction spaces to simplify this diagram into this one. So the whole point of this operation is just to say that you can do several changes of basis that take you from this one to this one. And since this is the one we wrote the initial states in, then it gives you explicitly the action of this operator. Okay. Before doing an explicit example, I will just now explain how the symmetry lines act on this and why they commute with the Hamiltonian. Yeah.
Does this allow you to build a single Hamiltonian or a whole phase?
So it really, like here we have, no constraints on the Hamiltonian, I would say, apart from the symmetry. So it can be anything. So it's a potentially a Hamiltonian that will describe the different gapped phases, by tuning the parameters there. It could, yeah. So there was really no, as far as the physics is concerned, the only thing that we, apart from like of course some locality or whatever, the only thing we constrain is the symmetry. It can be anything else. Okay, let me just do the symmetry lines over here. So the symmetry operator. So I'm just going to give you sort of the answer, but you can sort of demonstrate. Let's say if you didn't know what the symmetry was like, you could literally like work it out. So the symmetry operators, they are going to be given by lines in this so-called Morita dual with respect to M. And the way they act on the system is from the bottom, actually. So it's literally a topological line, and it's literally a line here labeled by Y. So this is in the Morita dual. Here it's in C, here it's in M. And the action is also done graphically by using like some graphical operations, so using like completeness relations of junction spaces and things like this. So how it looks like. So of course it acts in the same way everywhere. I'm just doing it locally, like in this neighborhood of two sites. So first you want to use some kind of completeness relation in order to, well, let me draw it and then I will explain what I mean. Okay. Okay, so what I'm using here. Okay, first of all, why can I do this? This thing represents a map. Remember, it's written somewhere. It's a functor from M to M, so it's basically something that takes degrees of freedom in M to degrees of freedom in M. So here, graphically, I have something in M over here, in M over there, and then I have this object, this functor that just like maps an M to another, an object in the module category to an object, another object in the same module category. So it makes sense to have access to junction spaces of this form. And here what I'm using, it's literally an equality. I'm just using some completeness relation of the junction spaces that appear over there. Now what I want to do is that so same story, now I want to express this object over here in the original Hilbert space in order to write down the action as explicitly as possible. And I can do that by using the move that is at the very top there, which allows you to pass a line given by the Morita dual, pass an object in C, right? It's this kind of commutation relation of the action with the action of an object in C. And so this, when you do this, then you can get something that looks like this. Okay. So I just move this one, if you want, on the other side of X there. So I'm using repeatedly this omega, this module structure of the module functor. And then I can just simplify the diagram using the orthogonality condition of, okay. So now, of course, I mean, let me maybe emphasize this. When you do these moves, you have some sums over intermediary labels. So it's not saying that this is literally one basis vector, and it's typically going to be a sum of basis vectors when you work it out. It's the same as when you write down, every time I write down an arrow like this, and you have to sum over the labels that show up on that side, and it's a basis transformation. Okay, and now the commutation relation. So this is the action of the symmetric operators. Now the fact that it commutes, the commutation relation will follow. Let me put it here. The commutation relation follows from the pentagon axioms. Okay, and the way it works is the following. Let's say you take, I look at the action of the Hamiltonian. Remember that it's given by this diagram. Okay, and then I have the symmetry that acts from the bottom. What I can do is that I'm not going to use the completeness relation in the middle just yet. I'm just going to use it over there, like this. And now the question is, so then I want to go from this, right, to something that looks like that. Okay. And they have my junction space. This is one big junction space here involving 4 lines, right? I can express these vectors in terms of these ones. Maybe let me just remove this. So this is a well-defined vector in the junction space. And in order to work out what it is in the original basis, well, you can do it either, you can first kind of take care of the action of the Hamiltonian, you can first kind of simplify this part exactly in the way we did it when defining the Hamiltonian, or you can rather use first the completeness relation of the lines and then takes care of the action of the symmetry. And you can do it in any order, and the fact that you can do it in any order will follow from the pentagon axiom that are satisfied by the module structure. So in a way, it's just a consequence of this MacLane theorem that was mentioned yesterday. It's just like if the pentagon axiom is satisfied, then basically whenever you have some diagrams, you can sort of manipulate them in every order that you want, and it will always give the same answer. Yeah. Okay, so now let me use this framework in order to do an explicit example. I'm going to revisit the cluster state model from this using this framework.
Sorry, before you move on, this shows that any Hamiltonian of this form will commute with the symmetries.
Yeah.
Is it clear that all nearest neighbor Hamiltonians that respect the symmetry have to be of this form exactly?
That's a great question. So I would say, partial answer. If you, let's say we have an ordinary symmetry, then you're looking for just some operators, right, that commute with the that are invariant under the action of a group, right? In that case, so the Wigner-Eckart theorem tells you that this operator you can always write it down in terms of Clebsch-Gordon coefficients, in terms of intertwining maps. Okay. Then, in that case, these guys represent essentially Clebsch-Gordon coefficients. So this is literally what we are using here. We are essentially decomposing a Hamiltonian in terms of Clebsch-Gordon coefficients. So in the group case, it follows readily from the Wigner-Eckart theorem. Now, provided that you have the right generalization of this theorem, this is the same statement in general. Yeah. But it doesn't mean it's easy, and yeah. Okay, so let's do the cluster state model. Okay, so what do I need for this model? Well, we already know this model. It has a Z2-Z2 symmetry. So this is going to be my starting point. So I'm going to choose the starting point to be this category. So D2. I'm writing D2 for Z2 times Z2. This is going to be my starting point. Let me introduce a few notations. I'm going to write the elements of Z2 as 0, 1, so I'm using addition modulo 2 for the group multiplication, and I'm writing a given element of D2, so as a pair of Z2 elements. Right? This group there is a choice of 2 cocycle in particular, which means it's possible to do there is a choice of discrete torsion. I'm going to write the trivial cocycle as 1 and non-trivial cocycle as psi. Okay. And this psi cocycle, there is an explicit formula for it, which is just given like this. So I'm using the notation that I have over there. So it's like the second component of G with the first component of H. Okay, so that's for the input category. Now I need to choose an object. This object is going to be the direct sum of all the possible objects, of all the simple objects, sorry. Okay. So it's basically the direct sum of the group elements, if you want. And the operator is going to be defined like this in a very explicit way. So I'm going to So first of all, I'm conflating sort of the group element and the corresponding here vector space. It's a bit more convenient. And I'm writing down explicitly, instead of using x, I'm literally summing over the corresponding group elements, so writing down as explicitly as possible. So I'm writing it down in the basis I introduced over there. Well, remember that the sums are all modulo 2. Right. So here I'm choosing essentially, so I can choose freely the coefficients I'm putting there, the edge coefficients. Here I'm making this choice, which will become clear in a second. I'm just choosing these phases there. And as far as the object y is concerned, I'm essentially choosing only 2 of them, the one given by 0, 1 and 1, 0. Then since the junction spaces are all one-dimensional, once you have a G here and then you choose this one there, the one at the top has to be the sum of the 2, because that's the only way to get a non-vanishing junction space, right? It's just literally just group multiplication, right? Okay. So now we still have to choose a Hilbert space, and we have several possibilities. I'm going to go over some of them, not all of them. But the simplest one to start from, this is the one that we sort of mentioned earlier, is like when you can choose the module to be vec, then we know for a fact that we're going to get a tensor product space. So it's going to be the simplest case to consider. So I'm going to start from this one. So I'm choosing the module to be vec. So more explicitly, how does the Hilbert space look like? Well, it's quite simple in that case. I'm going to represent, so in vec there is a unique object. So I'm going to use this dashed line to represent that there is no freedom there.
Yeah, very stupid question. You had vec G and vec psi.
Yeah.
Which one are you talking about now?
Okay, so vec psi as a category was just vec, right? So it has a unique object. Okay, I wrote the psi because it's also a module category in that case, and the F symbols of the module category depend on this choice of psi. So I just put a psi to keep track of it, but it's just vec, right? So when I put just vec, it means there is it's basically there is a unique simple object. It's just the one-dimensional vector space. So I'm not, yeah. I prefer not to draw a line explicitly. Okay, and here, so I'm going, instead of writing x in the spirit of the way I wrote the Hamiltonian, we have all possible simple objects, so all possible group elements showing up in x. So I can do the span over these group elements, and I get something that looks like this. So I have the group element G at the site 3/2 and so on. Okay. So this vector space is, in that case, literally a tensor product space. I have copies of C4. I have a 4-dimensional vector space locally because I have 4 group elements in my group. And I'm going to make now a choice of sort of...
I'm confused.
Yeah.
Before you were putting X on top.
Yeah.
And now, so this would mean that these states occur in some particular combinations. And now you're just taking them span linear.
So the thing that X, when it's not a simple object, it means that if it's not a simple object, it means that even, let's say, even if I choose vec there where there is no freedom, if these are 4 possibilities, right, it means that essentially that I have a 4-dimensional space over here. So instead of trying to write down in terms of vectors or whatever, it's easier to just keep track of the corresponding group element. Yeah, that's just... okay, and now I'm going to choose a sort of, for C4, I'm going to write the basis. I want to get something in terms of Pauli operators eventually. So I'm going to write down C4. I'm going to use the Pauli X basis. Well, basically, I'm identifying, let's say, if you have the group element 0, 0, right, I'm saying that this is the same as having the state plus plus in this 4-dimensional vector space. Okay, and now I can write down the action explicitly in terms of spin operators. So how does this Hamiltonian HI act? So let's investigate a little bit. So basically, then you can, in that case, this diagram, essentially when you choose vec, you can literally interpret this diagram as the action of the operator. It's basically going to take the state labeled by G and the state labeled by H to the state labeled by G plus 1, G plus 0, 1, H plus 0, 1. Okay? And it will come with the phase. Okay. This minus 1, it depends on the first component of G. Writing, since I'm working in the Pauli X basis, I can basically capture this coefficient here with the Pauli X matrix. It's going to give me the right sign. So concretely what I mean that this operator acts in the following way. Okay, so the sigma z's, they take care essentially of, so this is the first part here is the one on the left, the second part is the one on the right. The sigma z's, they take care of the multiplication by the group element 0, 1, here by 1, 0, and then the Pauli X there, they capture these phase factors that I put by hand in the definition of my Hamiltonian. And this, so here I'm treating my system as a, where my local degrees of freedom are effectively pairs of spin 1/2 degrees of freedom. If I rather think of it as just like the Hilbert space, which is a tensor product of spin 1/2 degrees of freedom, this is literally the cluster state that Schurren consider. So I can rewrite essentially, effectively, this is literally the same thing as this. Okay. So just to illustrate how you recover like a simple model within this framework. Now this model has obviously a Z2 symmetry, which in my framework, so how does this arise in the framework? It's going to be the dual of vec D2 with respect to vec, which is equivalent to rep D2. So of course it's an abelian group, so representation of the abelian group, it's equivalent to the group itself, but I want to keep track of this representation of D2. It's good to keep track of it. And it's generated, of course, by just the Pauli X operators on even and odd sides, exactly like we saw before. Okay, so now let's see what happens if I make a different choice of module category. So I'm doing it maybe slightly backwards in the sense where sometimes the easiest scenario is to start from the module category to be the category C itself. Here I chose already one that is vec, it's not the category C itself, so now I'm going to do the one where we choose M to be the category itself. And the way this will be interpreted, this will amount to essentially gauging this rep D2 symmetry of this model. Okay, so now I'm choosing, so everything stays the same. My Hamiltonian is defined exactly, or I would say my abstract Hamiltonian that is defined over there, which is just a vector in some junction space. This is literally the same. The object X is literally the same. I'm just changing the module. And the claim is that by just changing the module, this amounts to performing gauging of some of the symmetry. More precisely, it's going to perform the gauging corresponding to the algebra object, which gives rise to this module category. So the only thing we need to look at now is, so how does the Hilbert space, how is it modified? So now I have non-trivial degrees of freedom at the bottom, right? Because they are everything, it's all group elements. Okay. So what I have a span, so here I have a group element, it's G1, G2, G3. And a bit in the same spirit as the way the Hamiltonian operators are defined here. Once I specify these module degrees of freedom G1 and G2, well, of course I could put X here and look at all possible combinations of group elements, but I know immediately that there is only one outcome that is valid, is when the one at the top here is G1 plus G2. Otherwise, you will not get a non-vanishing junction space, right? So it looks at first like maybe you have a non-tensor product space because you choose degrees of freedom over there, you have X, and then you have to put some constraints, which is to have a non-vanishing, you have to impose these fusion rules, essentially, to have a non-vanishing junction space. But there they are so simple that I can kind of solve effectively these constraints, and then I'm left really with the tensor product space. So this one here has to be G2 plus G3. Okay. So this thing is isomorphic to the one we had before. But now I'm thinking of the degrees of freedom are being basically just this, right? The others, there is completely fixed. So I have my tensor product space, but now if before it was on the half integer sides, now it's going to be on the integer sides. And we see actually a shift of the lattice by sort of half a unit, which is not innocent since we are doing gauging, right? Yeah.
Are your lines oriented?
Yes, everything is oriented. I didn't draw them, but yes, they're all oriented. The reason why I'm not drawing them is because you can sort of fix some conventions, and okay, if you have them in mind, then it's completely unambiguous. But yes, they are all oriented, yeah. Of course, here it's Z2, so you don't actually need to orient them, yeah. Okay, and so now, so I'm using the same basis for my C4. Huh? I'm still working in the poly X basis. And now how it acts, so the same operator, it acts now in a different way. So let me write it down, and then I can explain a little bit. So we get something that is very similar looking. Okay, so it's slightly more difficult to read off why it acts this way. So if you look at the operator on the left here, so it acts on the vertical, so the group element G by multiplication by 0, 1. Okay, so basically it's going to act by multiplication by 0, 1 on this thing, right? But it's also going to act by action by 0, 1 on this one. And so if these two are shifted by the same amount by 1, 0, this can be effectively amounts to shifting G2 by 1, 0. Right? If you shift this one, if you multiply this one by 1, 0, it will multiply this one and this one by 1, 0 as well, because G2 appears in both cases. Right? So this is why the action, not the Z there, this is really, this represents the multiplication by 0, 1 acting on these degrees of freedom. So what we recognize here is that it's essentially the cluster state model, if not for a change of basis. I swapped essentially the Pauli Z and Pauli X. And this is not, since I kept everything the same, this is actually not very surprising, because the symmetry now, the symmetry would be given by the dual of vec d2 with respect to itself, which is vec d2 again. And the symmetry here, since there is a change of basis, the symmetry is actually generated by, not by the Pauli X operators anymore, but by the Pauli Z. Oh, sorry. And so this trade-off, the fact that we traded Pauli X and Pauli Z, we could have kind of predicted it, because strictly speaking, you see the Morita dual, now it's vec d2, while here the Morita dual was rep d2. So even though it's all isomorphic, the fact that we trade vec d2 for rep d2, it reflects this change of basis that naturally appears when you fix everything.
Is it integer label or half integer?
Yeah, no, actually, Oh, no, but wait, I rewrote the exact, okay, sorry. I rewrote exactly the same Hamiltonian, my bad. That was probably confusing. I skipped a line. Somehow I managed to explain it anyway, but okay, this is... yeah, that's a good point. Okay. Okay, my bad. That makes more sense. So the action by 0, 1 was it's given by the Pauli Z, so it had to be in the second component. Okay, let's do one last case, which is the most interesting one. So maybe just to clarify, as I mentioned before, choosing this module category, so compared to the initial choice that we made, where we had chose vec, and then we have the rep d2 symmetry, I'm not fully demonstrating it, but I'm claiming that choosing this one instead amounts to gauging the rep d2 symmetry. Now gauging, a D2 symmetry amounts to performing Kramers-Vanier on the two Z2 components of your model. And Schuring mentioned before that the cluster state model was self-dual under Kramers-Vanier. So this is exactly what we are recovering over here. So now I'm going to do another essentially gauging operation, which will amount to a twisted gauging, and we will cover the Kennedy-Tasaki duality. So I'm choosing this module now, which is VEC psi. So I had this notation before. Let me now clarify it a little bit. So remember that, so as a category, VEC psi is equivalent to VEC. But as module categories, they slightly differ, and they differ by the fact that VEC has, I didn't specify it, but VEC, it has a trivial, there is a trivial F symbol associated with VEC. Same story as here. We read off, the reason why I was able to read off immediately the action of the Hamiltonian without relying on my kind of graphical calculus is because the corresponding F symbols were all 1, right? So then you can sort of bypass the usual definition. Here it's not the case anymore, where I have the following F symbol, which is given by the 2 cocycle, right? So basically when you change basis here, there is this choice of phase that we can make, and this choice of phase is given by the 2 cocycle. Okay? And I gave before the explicit definition for the 2 cocycle. The Hilbert space in this case, because as a category it is VEC, it's the same as the one we had before, the one for VEC, right? So this was the one where we had copies of C4 on the half integer site. And now let me work out. So now we have to be a bit more careful as to the definition of the operators, because we have non-trivial F symbols, so we have to use the general definition which I had somewhere before. So let me I will do the first operator, and not the second one can be deduced accordingly. So I have this. I have this prefactor here that I'm reproducing, and that was the definition of the operator on the left. Okay. So now what I'm going to do is that I'm going to do one move like this. So there is no sum involved. In that case, it's just like we have to keep track of the corresponding phase factors that show up. So I have H1. This one, in principle, comes with a -1, but in that case, it wouldn't make a difference because it's just plus or -1. But I'm just going to write the inverse explicitly anyway. Okay. So it simplifies a lot, the expression we had before now. And now I'm doing it a second time. I'm doing another F move, which gives me a slightly different coefficient. Okay. And we are back to the original. I'm skipping the step where you're popping the bubble. You're just using the orthogonality condition because it's trivial in that case. So I wrote down the definition before for this psi. Let me reproduce it here. Okay, and then you can just check that this whole thing is equal to -1 to 2 times H1, which is just 1. So basically, choosing this different module category that depends on psi completely sort of cancels these phase factors that I put by hand when defining the Hamiltonian. Now, what does it mean to get rid of these phases? Well, if you go back to the definition of the first Hamiltonian, it amounts to just removing the Pauli axes, because the Pauli axes were responsible for these signs. And so if you remove the Pauli axis, you find that HI just acts as which is just a ferromagnet. So this is a Hamiltonian for a D2 spontaneity symmetry broken phase. Okay. So this is this Kennedy-Tasaki duality, this twisted gauging, where we started from a model that has a D2 symmetry for an SPT phase. This is the cluster state, and it was established before that the cluster state was a representative of the D2 SPT. And by doing this twisted gauging, I can go to a ferromagnet, which is just a representative for a D2 spontaneity symmetry broken phase.
I'm kind of confused. I thought choosing this modulo category would have been equivalent to stacking an SPT. So I thought we would have just gotten a trivial ferromagnet. Why did we get a ferromagnet?
So actually what this amounts to is rather doing gauging, pasting the SPT and gauging again. The thing is that the additional gauging, so as soon as you gauge, as was established before, you project, you have this projector, the Kramers-Vanier, right? You project onto the even sector. So if you do Kramers-Vanier again, the only thing that it's going to do, at least in this picture, where here, in this picture, when I'm doing Kramers-Vanier, I'm going from integer size to half integer size, a bit different than the way Schoring did it, where it was really sort of on-site. Here there was this shift. So when I do twice Kramers-Vanier, I'm already projected onto the even sector anyway. So the only thing that it does is that it's going to shift back to the original lattice. So you can kind of do it for free. So here by twisted, because I'm doing it from vec to vec psi, then it amounts to doing Kramers-Vanier, pasting, and Kramers-Vanier again. If rather you go directly from vec d2 to vec psi, this is more literally just twisted gauging, where you do the twist plus the pasting. You paste the SPT plus you do Kramers-Vanier. Because as you see, since this is self-dual, if I go from vec d2 to vec psi, this was also the SPT. So this is more literally, I would say, what twisted gauging is. Okay. The reason why it's convenient to do it like this, from vec to vec psi, and this is the last thing I'm going to explain, is because then it's particularly nice to write down the operator that performs this operation. So we could do that for Kramers-Vanier already, but I'm going to do it directly for this case. So I'm claiming that this Kennedy-Tasaki duality, depends a bit on how you define it, but if I define it as going from SPT to spontaneously broken, then I can take this as my definition, as the operation that takes you from the choice of module vec to the choice of module vec psi. So this is something that maps, it's an SPT to spontaneously broken. And the corresponding, the KT operator, so here what it's going to be, well, it's going to be, as I mentioned before when we were talking about interfaces, it's literally going to be a map between the corresponding module categories. This is what the operator is going to be. So KT operator is given by, in that case, the unique simple object in, so this category, so I didn't use exactly this notation before, but so this is the category of functors from vec to vec psi. I'm just going to give you the answer. You can show, and it's a nice exercise, to show that this is equivalent to the category of projective representations of D2. And there is a unique element, there is a unique decomposable projective representation of D2, which is, I'm going to write it pi. Okay. So somehow, I know that from this pi, from this projective representation, I can cook up the operator which on the lattice will perform this operation. The way to do that is given directly by so the definition of this guy. These are maps. So first you have a map from vec to vec psi, and then you have these omegas that are these module structures that allows you to change, to do this recoupling. So let me give you explicitly, so given a pi, you can write down explicitly what is the corresponding module structure of this functor. And it looks like this. So my functor is given by pi, okay? here I have my object in my original category. It's just some group element, right? And this projective representation is two-dimensional. So I have actually here, I have a magnetic index, right, to keep track of the fact that this two-dimensional is because this junction space is two-dimensional. Okay. So here at the top, this dashed line I represent, it's a unique simple object in VEC. Okay, and at the bottom, well, it's still a unique simple object, but if you want, it's rather in VEC pi, right? I'm moving from VEC to VEC pi. At the level of the Hilbert space, it doesn't do anything because as a category, VEC and VEC pi are exactly the same. Now you can write down explicitly what happens when you can explicitly write down the change of basis. And it's simply given by the evaluation of the projective representation on G. Okay. So this is just my representation matrix for G, and these are the magnetic indices. G. Okay. So now I can use that to, so the way this duality operator acts, they act essentially exactly the same way the symmetry operator acts. The only difference is that, so using the, well, I have a piece of it over here, they act in the same way. The things that as they act, they will also transform the module degrees of freedom. In principle, they do. Here, since as a category, the two module categories are the same, actually they won't modify really the degrees of freedom. They will just, they act, in that case, it acts diagonally, if you want. So let me do this. So let's look at this configuration where I have G here, H there. I have two group elements, right, at two neighboring sites. And I want to act, so exactly I have a topological line, right, which is labeled by pi, and the action is given like the action of the symmetry line. And in a way, a symmetry operator is just a special duality operator where you're going from the same module, from a module to the same, right? So let me write it down explicitly. We get something like this. So I'm first using the completeness relation. So completeness relation here, it just means that I'm summing over the same basis vectors. Okay. And now I'm going to use so L times this operation to move a pi line past a line labeled by a group element. So I'm just doing it locally. Here you can infer how it looks like on the whole space. Okay. Okay. Let me put it at the bottom. Okay, so I just move, you see, let's take this branch here, this line. I move it past the G. As I'm doing that, I'm collecting a pi G for the corresponding magnetic indices. This pi G, UV, and then here I can just, in that case, it's just the orthogonality condition of the basis vectors. So this simplifies in the obvious way where you can just sort of remove that bit. So I can rewrite more in symbols what this operator is. So the duality operator KD Tasaki, so you can write it down very conveniently as a matrix product operator, the language that Shureng used at some point to rewrite the Kramers-Vannier operator. And in that case, it's given by this very simple expression. And it's immediately actually in the matrix operator matrix product operator language. In that case, you don't even have to work really hard. G12. Okay, so this is, it acts diagonally. So it doesn't actually modify the degrees of freedom, but you pick up some coefficient. Okay. So it acts diagonally, and this is what this part means. But then you get this contribution that depends on the value of the group elements, where you're evaluating all the group elements. You take the product of this of your matrices of the projective representation, and finally you take the trace. So this is literally what this presentation means.
So the extra qubit that Shufeng added here is this two-dimensional vector space for the projective representation of this. Is that the interpretation that has?
So Shang was doing it slightly differently, right? Because he was like he was not exactly the same manipulation because he was doing like with the Kramers-Vanier, right? Well, here I'm doing, as I said, it's kind of more like doing it twice and so on. So let me just make one comment, and then I will, which is related, and then I will address that point. Let me just put it there. Will be my final comment. Is that from this expression, you immediately see, so this is a non-invertible operator, and you see immediately that this is a non-invertible operator from this operation. And the reason why is because, okay, you can sort of simplify this expression by taking all the products of this projective representation. So then you end up with like one trace of one matrix, which is evaluated on the product of all your group elements. But, and this is just by definition of the projective representation of D2, the only way for this trace to be non-zero, G must be the identity. What it means? It means that this operator, so yeah, this operator projects onto the even sector, the even sector, right? So it projects onto the even sector. So this is why it's non-invertible. This way it's non-invertible. But in particular, if you restrict to the even sector, it is invertible. Now, if you want to access the different sectors, this is why you need an additional degrees of freedom to keep track of these additional sectors. And then you can actually make this operation invertible on this like sort of larger Hilbert space where you have this defect essentially that controls as well the corresponding sectors. So I think this is.
But is this the junction of pi or not? Is that Hilbert?
So I don't really remember actually what was the analog in ensuring discussion. What I've just referred to was the fact that so whenever I have my Hilbert space, I can just insert a defect like this, which is going to give you twisted boundary conditions. So then you have an additional degree of freedom there, which you can have in the MPO, and this will give you all the operators for the given sectors, right? But I don't really remember exactly in which context you had this additional one, so I don't. Yeah.
Okay. And then for the future, there would be another horizontal guy and the vertical guy sticking up.
Once you introduce defects, so exactly the picture that Yifan had, you recover it exactly on the lattice. Once you put a defect like this, then the symmetry operators, they have to kind of combine with these defects, right? So you get this tube algebra and you recover exactly the same.
Yeah, I was wondering what was to the right of the photo you drew? Is it another horizontal line and then an up?
No, because here okay, I see what you mean, like over there. Yeah. No, it doesn't. No, it ends from the bottom there. So you get you can potentially get an additional degrees of freedom corresponding to this junction space here, but you're not picking up an additional sort of at the top here. Yeah. Okay, so that's essentially what I wanted to say, but let me just maybe wrap up. So just to say, okay, was to emphasize the fact that the machinery that makes sense in the continuum also applies in the lattice. All this like language of algebra objects and module categories, you recover it explicitly on the lattice. And the point of this framework is that, well, first of all, once you recast a model in this framework, so for instance, this showing talks about the rep D8 symmetry of the cluster state model, right? So if you start from rep D8, and if from rep D8 you can write down essentially the cluster state, then you will know immediately that it has a rep D8 symmetry. Right? So it can be a way sometimes of like sort of proving, of checking immediately that a given model has a symmetry. Sometimes you don't even really know what you're looking for, but then you're starting from some system, you're doing some twisted gauging, then you know by construction that it must have a certain symmetry, even though it's not necessarily obvious, but you just know it's there. And then it's just a matter of checking explicitly that you indeed have that symmetry. But the main point of this approach also is to be able to sort of bypass some of the operations that you would do by hand when you do gauging, where it just amounts to a change of module category, and then you can recover all these stories, or like in particular Kennedy Tasaki and so on. Okay, I'll stop.
Just two questions. So just for sure, it's clear the STS or TST.
Yeah, so this is the same, right, in that case.
But the operator is different, right?
If you do one.
So the STS, the corner division is like 4 TST.
So here, okay, so here it would amount to STS, right? It's STS. You do it twice gauging, and yeah. As I said, you can just do TS as well by just doing. You go directly from vec d2 to vec psi. Here I did it this way because this is exactly in the way also Schureng had the two Hamiltonians. So this was to recover exactly the Hamiltonian.
And also the way also to the open boundary.
Yes, you can do open boundaries. I mean, I just mentioned very quickly here the twisted defects, but you can do everything in terms of twisted defects, which is more subtle, and then you can do the same in terms of open boundary conditions as well. Yeah. Okay, thank you.